this video, we're going to contrast the approaches to solve linear and quadratic equations, and then we're going to start to talk about factoring quadratic expressions, which will be needed to solve quadratic equations. That'll be one approach we'll discuss for solving quadratic equations. So first off, for linear equations, we know how to solve them well now. You just use your basic properties of equations by adding or subtracting the same number from both sides, and then multiplying or dividing the same both sides of the equation by the same non-zero number. So for instance, for this first equation, you see 2x plus 1 equals 13. We know the steps. Subtract 1 from both sides, and then divide by 2. So we know that x equals 6 is the solution. Looking at these other two equations, these quadratic ones, okay, they're much more difficult because you cannot isolate the x. You can't combine the x squared and the x terms. Okay, we don't know what to do. All right, we can't just use our basic properties of equations to solve. And the second equation, it looks simpler than the first, but it's even tougher. Okay, just another word about those. You might be able to guess some of the solutions to the first equations. You start poking around by plugging numbers in, you might get the solutions. You might find that 2 is a solution, negative 4 is a solution. But making that subtle change by changing x equals, or changing the 8 on the right hand side to a 5, makes the situation much harder. You're never ever going to guess at the solutions to that equation. It's going to need entirely different methods. The first quadratic equation there, we're going to be able to solve by factoring. The second one, though, we won't be able to. And that's one of the drawbacks to the factoring method. When it works very well. It's a pretty clean solution. When it doesn't, though, we're out of luck. Okay, so now we're going to move on to talk about factoring quadratic expressions of the form ax squared plus bx plus c. And we're going to do this by breaking it into two cases. One, where the coefficient of x squared is assumed to be 1. So we're really just looking at this kind of polynomial, x squared plus bx plus c. Now, what do we want to do? We want to be able to factor it. All right, factoring is going to mean the same for polynomials as it does for numbers. We're going to want to express it as a product of two smaller polynomials. And by smaller, we mean polynomials of smaller degree or lesser degree. So in this case, we want to take our polynomial, x squared plus bx plus c, and write it down as the product of two smaller ones. And if that's going to be the case, they're going to have to be linear polynomials, degree 1. We have to have an x plus a number, an x plus a number in each case, in each factor, because we know we have an x squared. We're starting out with just a single x squared. There's no number in front of x squared besides 1. All right, so we have to have an x term and an x term here to multiply to give us an x squared term. Now, if this is going to work, if we're going to be able to find a factorization, when we multiply this out, it must check to give us c and bx also. So if you multiply the polynomials together, you end up getting x squared plus px plus qx plus p times q. And then we're going to, from there, equate the coefficients. Right? So we have that the coefficient of x is p plus q, and the coefficient of x must be b. The coefficient of our constant coefficient is p times q, and that's also supposed to be equal to c. If that's going to be true for every real number, x that we plug in, we must have that c is equal to p times q, and b is equal to p plus q. All right, so what does that say? What should we do? We should look for factors of c, our constant term in our polynomial, that add up to b, which is the coefficient of x. All right, and that's why we do it. If it's going to factor, that's what we have to do. That's what we're going to have to find. And we're going to assume in these examples that the numbers b and c are integers. If they're fractions or if they're square roots or something else a little harder, then it becomes much tougher to do. All right, so we're just going to assume that these coefficients are integer values. Okay, now let's apply those ideas. For this first example, the constant term is 6. The coefficient of x, b, is 5. We're looking for factors of 6 that add up to 5. And we know 6 is equal to 2 times 3. And 5 is 2 plus 3. So what does that tell us? We can factor our polynomial x squared plus 5x plus 6. as x plus p times x plus q, and that's going to be x plus 2 times x plus 3 for us. Okay, and you can check that by multiplying it back out. Just one thing you want to make sure is that the x term adds up correctly, and it will there. For the second example, your constant term is -8. Your coefficient of x is -2. All right, in this case, we're going to rewrite -8 as -4 times +2. All right, there's other combinations, but that is the pair of factors of -8 that add up to -2, and that's what we're concerned about. So we're going to be able to factor our polynomial x squared minus 2x minus 8 as x minus 4 times x plus 2. Okay, we couldn't think about that as x plus -4, but it's just shorter to write x minus 4 and then times x plus 2. Okay, the next example we're going to look at is x squared plus 7x minus 60. Now for this one, the constant term -60, it has lots of combinations, so we got to be careful here. Think about the number 60, and then b, our coefficient of x is 7. Just looking at the number 60, forgetting about the minus sign for a second, think about all the different factors of the number 60. You can write 60 as 1 times 60. You can write 60 as 2 times 30, 3 times 20, 4 times 15, 5 times 12, and then lastly, also you can write that as 6 times 10. So what we want to do is look at these pairs and think about adding and subtracting those factors together such that we can get 7. And by adding and subtracting, the only pair we can get to 7 is 5 and 12. All right, now we got to consider our signs now. -60 we can write as 12 times -5, and those two factors added together to give us +7, which is what we want. So that leads us to our factorization. So let me clear some space and then write this out. We can now factor as x plus 12 times x minus 5. Again, that could be x plus -5, just briefer to write x minus 5. Okay. All right, now going back up, let's take a look at our last example here. In this case, our constant term is 20. Our coefficient of x is -9, so we want to know, are there two numbers that multiply to give us +20 that add up to -9? In this case, it's going to be -4 and -5. Okay, two negative numbers multiply to give you a positive and add to give us a negative number in this case. So we're going to have x squared minus 9x plus 20 is equal to x minus 4 times x minus 5. Okay, a couple things worth pointing out. Each of these examples illustrated a couple of the sign conventions. So if the c term is positive, then both of your factors must be either positive or negative, and that can be determined for you by the coefficient of x. So if the constant term is positive, they both have to be positive or both have to be negative, and then it'll be determined whether they add up to a positive number, like in the first example, or a negative number, like in the second example. For the middle two, where the coefficient of the constant term, was negative, one of your factors has to be positive, the other has to be negative, and that will be determined to you by whether your coefficient of x is positive or negative. You're going to have to take the plus or minus sign to go with the larger or the smaller number to get them to add up appropriately.